I'm Dr. Michael Riordan. I'm a cardiac surgeon from the Houston Methodist Hospital. I'm here today with two good friends, Chris Meduri, an interventional cardiologist from Karolinska and the Chief Medical Officer for Anteris, and Azim Latib, an interventional cardiologist from New York. And we're going to talk about a very novel balloon expandable valve. So Chris, why don't you start off by telling us a little bit about this new technology and this new valve?
Yeah, well, guys, it's great to be here together today. So I think this is really an interesting, transition in our space of TAVR. You know, as we look at the history of this field for the last 10 or 15 years, I think we know we had two interesting platforms, both the balloon expanding intraannular valve and these supraannular valves. And we knew the trade-offs that we had with each one, both of their own strengths and weaknesses. Anteris' DurAVR valve is really a combination of these things that we think even further strengthens the ability to treat our TAVR patients. It is the first-in-class biomimetic valve that actually takes a single piece of bovine pericardial tissue, and instead of just actually putting that in the valve, it actually molds and shapes that single piece of bovine pericardial tissue to the shape and look of a native, healthy aortic valve. And because of that, we are now seeing results clinically that look like a pre-diseased state. Excellent hemodynamic performance, very nice laminar flow. And I think one of the really nice things about this is it is incredibly easy to put in. It is pre-mounted on a balloon expandable platform, and so it is just into the body, across the valve, and has in addition a unique feature of commissural alignment that we can uncouple the delivery system and easily rotate the valve there. And as we will talk about a little bit later, we've seen really unique results in our first in human experience, where we've seen really superior hemodynamic performance and superior flow, laminar flow that we've seen, we believe, because of this unique biomimetic shape. So we really think this is the first in a wave of technology that can really transform how we treat TAVR patients.
So a balloon expandable valve with self-expanding hemodynamics is like the holy grail. So do we have any data on this, Azim?
Yeah, Mike, I think we do. There have been two data sets of patients treated. So there's the initial first in human 20 patients that were treated in one site in Tbilisi, really showing great clinical outcomes and excellent hemodynamic outcomes. And then we got our own experience in the US. We did a 15-patient EFS in 7 sites. So I got to implant the valve myself. And this is a balloon expandable valve. It's easy to implant, easy to position. The commissural alignment that Chris mentioned was not difficult to do. And so we had a 100% success rate of implantation during the US study. The clinical outcomes at 30 days were also good. No strokes, no vascular complications, no deaths. One patient got a pacemaker, but 2 months later, from underlying conduction disturbance. So overall, really excellent outcomes that we would expect with a balloon expandable valve. I think the thing that took us back the most was when patients came back at 30 days and we started seeing the hemodynamics. Because let's face it, we're all in this era now where we're thinking about lifetime management. Can we implant one valve for the lifetime of that patient? And potentially, when you see the hemodynamics that we've seen both initially and then maintained at 30 days, it's been very impressive.
So these hemodynamics, were we getting this from patients with big annuluses, so it was easier, or were these patients that tended to be on the more difficult side with small annuluses?
That's a great question. The mean annulus diameter was about 22.3, and what we're seeing is single-digit mean gradients, and EOA is above 2 for an intraannular technology in a small annuli. And I think I've not seen that with any technology thus far.
So those are some difficult patients. I mean, Chris, what have you seen in the hemodynamics and the flow that you've gotten with this valve?
Absolutely. Now, so, like Azim has alluded to, consistently hemodynamics with mean gradients under 8, with EOAs at 30 days well over 2, and these are in core lab adjudicated patients. And I think the other thing, again, that's really exciting, excellent DVI and laminar flow. And we've seen this on cardiac MRI imaging now that shows, we've seen from bench to clinical practice, this flow that is just unlike other valves. And they've now presented data here, I think last year, that showed, unlike any other surgical or transcatheter prosthesis that actually provides quite turbulent flow traditionally after treatment, this flow is laminar. And so, again, I think this really is a different class of technology.
Yeah. Now, the heart cares about how much work it has to do, and laminar flow always costs less energy than that. When we started in our original TAVR series, my echo lab wouldn't even measure EOAs in surgical biomimetic valves because they were so hard to measure. They would only measure Doppler velocity index because it's so reliable. You don't have to measure the LVOT, you just get a ratio of flow above, below, and so it's a ratio of flow, so it's indexed to that patient's flow, and what it actually represents is the ratio of that individual patient's effective orifice area of the aortic valve to that individual patient's LVOT. So it doesn't change across valve sizes or patient sizes, because little patients have little LVOTs, big patients have big LVOTs. And you remember Becky Hahn looked at the core lab data from the Edwards trial and the Medtronic trial and found that the mean Doppler velocity index for S3 was 0.42 and for Evolut was 0.61. What are we seeing in this valve, Chris?
That's a great question. So right now, it looks like dimensionless index is significantly above 0.6, so 6.62, 0.63. So, like I think you're saying here, this is truly a different clinical result, and I think we will only continue to see the downstream implications of taking that workload off the LV, which I think our field is really just beginning to understand those longer implications.
So we know as surgeons for a long time, the bigger opening you start with, the longer the valve lasts before you get structural valve deterioration. Nazim, what do you think that's going to mean for this individual valve with these EOAs and this Doppler velocity index? Durability has to do with valve design and tissue science. What does this valve give us in valve design and tissue science that's going to get us there?
Well, Mike, I keep thinking that for a long time we almost looked at TAVR valves as having a class effect, right? We were treating aortic stenosis, trying to make sure we don't give patients pacemakers, get rid of PVL. I think we're now in a phase where we realize not all valves are created equally, and you can design a technology that hopefully will last the lifetime of a patient. And so when you look at these valves, sure, we'll have 10-year data, but until then, what is the best marker we can use that data is going to look good? And I think when we look at all technologies, whether they're surgical or transcatheter, being able to see at the time of implantation and 30 days, large EOAs with low gradients, I think that bodes well for the future of that valve and for the durability of that valve.
Just tell me a little bit about the tissue and how the tissue is prepared for this valve. Is it the same as the pericardial tissue and the other valves we see?
Oh, that's a great question, Mike. So it is actually quite a bit different process. It is a bovine pericardial tissue, but it is actually treated with this patented adapt tissue technology, which actually has been implanted now in over 55,000 patients worldwide and really has remarkable anti-calcification properties. I think also what's unique is because of this process allows us to do the molding. And as we've talked about before, one of the really unique things that may play a role in durability is this long coaptation length that we see with this valve. And we've consistently seen a mean coaptation length between 7 and 8 millimeters. And additionally, that also has led us to see that across bench testing, this valve doesn't pinwheel. And there'll be a paper coming out soon that actually shows that this, compared to every other valve out there, has essentially no pinwheeling. And I think pinwheeling may be one of these surrogates of durability that we may see eventually plays a role in some of the early degeneration that we have.
Yeah, so we know from surgery, from mitral valve repair and aortic valve repair, the length of coaptation really has an effect on how long valves last structurally. Well, it looks like we have a really exciting new biomimetic single-piece valve that may give us self-expanding like hemodynamics. Any final comments for the crowd?
Yeah, I would just say, look at the space, watch this valve. The thing I've been educational for me is that Anteris is a company that's been doing tissue for a long time. Many people haven't heard of them, but they've been around for over 10 years making tissue, so they didn't just wake up one day. But I think we're in this era where we can now hopefully start designing valves that are going to last for the lifetime of a patient.
So Chris, as Chief Medical Officer, plans for future trials?
A lot of plans for future trials coming, Mike. So yes, we've now finished the EFS. We're a lot of special access stuff across the globe right now. There's a pivotal trial coming on. We're planning things in Europe. So a lot of things in the near future.
Well, Chris and Nazim, exceedingly exciting news and data coming out. And I really look forward to as we launch these trials and see the continued data on this very unique and exciting valve. Thank you very much.
Thank you.
Thanks, Mike.